Hello, and welcome to Solving Electromagnetic Challenges, an EMA webinar series. My name is Matt Colding, and I'll be your host for today's presentation on PCBA design decisions and SI EMC consequences. To submit any questions you have during this webinar, please use the Teams Q&A feature at the top center of the Teams menu bar. After the presentation, we will address any submitted questions. Should there be any unanswered questions at the end of the webinar today, we will address them over email. It's my pleasure to introduce today's speaker, Ryan French, Computational Signal Integrity Engineer at EMA. Ryan French joined EMA in 2024 as a Computational Signal Integrity Engineer. His background is in physics, firmware, PCBA design, and SI EMC engineering, and gives him a unique understanding of electrical systems from the smallest details to the system level. Ryan received his bachelor's degree in physics from Saginaw Valley State University and his master's degree in physics from Montana State University before spending his time in the commercial aerospace sector. With his varied experience, he can tackle a wide range of E3 issues confidently while communicating the issues intuitively. Without further delay, I give you Ryan.
Thank you, Matt. Yeah, I didn't even think about that name, Saginaw Valley State University, but yeah. So welcome, everyone. Thank you all so much for showing up. Today, we're going to talk about a couple of design rules that you can use and the impact that these sort of design rules can have in your final product. We're going to jump right into the overview of this presentation. So first off, we're going to cover the two boards that I designed at EMA. I'm calling these the bad PCB design and the good PCB design, BPD, GPD for short. We'll go over their differences. After that, we'll go into 6 different types of analyses that really demonstrate how the differences in these designs affect the results that we're seeing. I use the tools ANSYS SI-Wave and EMA's own EMC Plus tools to do all of the analyses you see in this presentation. We'll chat about that at the end as well. But these pictures, a little taste of what's coming up. Starting out with the PCB designs. So the intention behind these is to create the same exact board, all the same components, the major components, microcontrollers and whatnot. And this board is just a generic platform for an ST microcontroller. It's got integrated power regulation and a lot of peripherals. We see here like an SD card. We have access to RS-422, very common in aerospace. We have some dedicated ADCs on this header here, Ethernet jack, some extra GPIO from the microcontroller, and a couple of USBs that we can use. So kind of a stand-in for any similar platforms that you're probably familiar with, like Arduinos or ESP32s. How did I make these boards? Well, I love free open source stuff. Everyone loves free stuff. So I use KiCad 9.0. This is the latest version. In 9.0, they added a lot of cool features like ODB++ export. And so take a look at it if you haven't used it before. All of the components I used come from the default KiCad libraries as well, so no very special components I'm using here. Calculating all of my design parameters, like trace impedances, I used this PCB toolkit, which you can download from Saturn PCB Design. It's a free tool, and it's got a lot of these tabs up here, a lot of neat little calculators you can use to help you set up your design before you jump into it. To create stackups, I went to Sierra Circuits. Again, you sign up with an email and you get free access to their PCB stackup designer. You put in the number of layers, the height that you want, and it'll generate a couple of stackups for you. Most importantly, though, I did no simulations or checks on these designs before I ran the simulations that you're going to see today. So everything that you're going to see are raw results just based on the rules and the design intentions I used between these designs. To complete the block diagram, we won't go into all of it, but we can power this board 2 ways, 28 volts, or we can use a USB-C 5 volts. These are regulated down to 3.3 and go through a current sense amp, just so we can tell how much current this board's drawing. You see a lot of peripherals. There are 3 EEPROMs on this, a RS-422 transceiver, a couple of 10-bit ADCs, a little bit higher accuracy ADCs, and a couple of headers, ADC header, microcontroller header, all that good stuff. In this table, we're just going to look at a quick comparison. And we'll go over the bad PCB design because everything that we list here is just going to be the complete opposite on the good design. And so starting off, the bad design has no power filtering, no common mode chokes, nothing like that. It also lacks a lot of terminations. There may be only one terminating resistor on the entire design. When it comes to decoupling, I used large size capacitors, poor placement, poor mounting to the board. Grounds, I split my grounds in the bad design. We'll see this, but I used an analog ground that the intention that I see a lot is that that analog ground is used for low noise applications with ADCs. We'll also dive into signal and return vias. Very few of them in the bad design, and no fill when I'm done, and we'll see the major consequence of that. Connector pinouts, there is a very high signal to return ratio on the bad design, which just means a lot of signal lines, not a whole lot of returns. And finally, the other major difference here is that I filled all of my signal layers with copper on the bad design, and I paid no attention to whether or not these are tied to a net. So a lot of them are just floating, just existing there. So we'll dive into the first analysis. We've got 6 of these to go over, and so it'll be a little quick going through this. If you have any questions, bring them up, put them in the chat. We'll talk about them at the end. What is it and why do we care about PDN impedance? Well, when an IEC switches a digital signal, it has to pull that immediate need for current from the network that's supplying it. This includes your regulator, the bulk capacitors, the planes, the decoupling capacitors, and even the on-die network of your chip. So as you're pulling this current through this network, there is some inherent impedance in that network, and that voltage drop is going to propagate, and that's a lot of noise that you could be creating. This is a huge part of generating near-field radiated emissions, but also a lot of other things like crosstalk is a major one, like far distance crosstalk that's hard to track down. In these simulations you're going to see here, I've made the assumption that I want my noise to be less than 5% of my voltage bus of 3.3 volts. So the result that we're going to look at is something like this. So if we look at this plot, there's an inherent limit to the impedance that you can calculate. And then when we plot the actual impedance for this IC, we're going to look for places where it crosses that threshold. So you see these 2 areas are violations. We'll also talk about the upper limit frequency that we have to care about. That's another important limit to know when you're looking at your impedance plots. What's the difference between these designs that really affects the results we're going to see here? The first is the stackup. So between my power and ground planes on the good design, you can see they're separated by 4 mils, right? They're very, very tightly coupled. And in the bad design, it's about 11 mils or so. And you see there's a signal layer in between, which further breaks up the coupling that we want between ground and power. In addition, I talked about decoupling. On the bad design, I used 0603 packages, which aren't that large, but they're larger than you need most of the time for decoupling. I used thin traces, and the vias to power and ground that you see here are really spaced far apart. That creates a large loop inductance leading from the planes up to that capacitor. Whereas in the good design, I use slightly smaller packages, 0402, very common. And I use these nice thick traces. Short traces going to vias, power ground vias are very tightly spaced, so further lowering that loop inductance. So how does this affect the results. We're going to look at two ICs. First is the Ethernet PHY. This is just the transceiver that sends Ethernet back and forth. And indeed, in red is the good design, and we see it's lower than the bad design, besides this little resonance here. I'd have to hunt down what that is, but it's well below any limit that we have, so we don't really care about it. But we see it's lower than the bad design, just using these rules. And there are a couple of little areas here where we might be violating that 5% limit in our good design. Bad design, obviously, lots of violations here. What we can do is, I made the assumption this is switching at 1 nanosecond rise time. If instead on the right we look at a 2 nanosecond rise time, we slightly shift our bounds just based on the calculations we do. And so instead of our upper limit bandwidth being about 500 megahertz, with 2 nanoseconds, it's about 250 megahertz. And what you can see is if we make the assumption that our rise time's a little longer than 1 nanosecond in reality, now both designs almost completely pass. The good design with lots of margin, bad design, maybe we're violating a little bit up at that switching frequency. Now the microcontroller is an interesting one. This has the most pins that are switching at any given time. And so you see the impedance limit is very, very small. I mean, we're in the milliohm range. And even at low frequency with 1 nanosecond, our bad design is already failing. That is not a good sign. And even up at the higher frequencies, this good design with the assumption of 1 nanosecond fails. Well, I'll keep harping on this, but even an experienced SI engineer following best practices, you may not pass. Without simulation, you may not know how your board is going to perform. And again, 2 nanosecond rise time gives us a little bit more margin, but we are still violating that limit. When you get results like this, you have to go back and kind of challenge your initial assumptions. Maybe all of my pins aren't switching at once. Maybe I can just assume half of them are switching at once, which is going to raise my impedance limit. Maybe my bandwidth frequency really is a bit lower than what we expected. So these are just some things to keep in mind when you're looking at results like this. The second analysis we're going to look at are resonances in the board. Why do we care about resonances? Well, noise entering our cavities, which is just space between two copper layers, it's inevitable. We'll always have noise. But we use this resonance analysis to see where in our design we are going to couple a lot of energy. And so what happens is we inject a 1 volt signal between two planes on a board, and we sweep the frequency. And then we look for the highest peaks. What frequencies are these peaks at? So at some frequency between two planes, we see this design has some really sharp spikes here. So that means at that frequency, if we get noise in there at that frequency, it's going to bounce around and resonate a lot in those areas, creating a lot of noise. And these resonances are just geometric. They depend on the sizes, proximities of your interconnects, also depends on the vias that you use. And so what rules did I follow for resonances? Via fill, this will come up again because it is very important. But on the good design on the left, red are the power vias I have, and blue are ground vias. And you can see there's a lot of them. I'm pretty far zoomed in here. Here's a capacitor size, and we've got a lot of signal ground and power vias here. I zoomed out on the bad board, and I have so few. I think I just used vias where I needed them for power and ground for ICs. So not a lot of return vias placed around. Something else that I did, again, I see this a lot, is splitting this ground. So this ground is an analog ground. The intention is usually this is going to be a low noise ground for our ADC signals. On the good design, it is one solid plane. And we'll see that here with the first results. So if we look at the resonances between the ground and power planes on the two designs, we see the major issue. This is the worst case in both designs for this cavity. And we see, look at the peaks showing up in that split ground this little split power plane here, that's a lot of noise. And so if we happen to inject any noise in this area at about 550 megahertz, which could be within our bandwidth, it's going to bounce around a lot. And that's exactly what we don't want on an analog ground, right? A low noise area. In the good design, it shifted up to about 650 megahertz worst case. And look at the colors. I mean, we're barely deviating from 0 volts here. This is a very low noise system. And that frequency might be outside of our switching range anyway, so we might not even have to care about this worst case. And again, a more interesting result here is if we look at the top layer signals with respect to the next layer, that cavity. On the bad design, remember, I filled these signal layers with a bunch of copper all over the place, and you can see all the noise developing in all these little islands that are floating about. That noise is going to bounce around in those islands and couple into any signals in the area as well. This is a way to introduce crosstalk. We'll talk about crosstalk next. And again, that split area just leads to a lot of issues that we want to get rid of. And on the good design, we see these really sharp peaks as well. This copper here is the chassis. And again, at about 600 megahertz, this might be outside of any bandwidth that we're switching. And so we may not have to care. And this is where your design intentions come into play. Maybe if this is unacceptable, this is a great way to add extra capacitors, extra bonding, or whatever to see how we can minimize the peaks in these resonances. So speaking of crosstalk, we're going to talk about the next analysis here. I assume most of you who are familiar with electrical engineering know about crosstalk. You'll know at least one of the mechanisms, but there's a few causes. The one that we're most familiar with is two signal lines, two traces in a board routed very close to each other for a long distance. Any energy traveling on one of these lines is going to couple over into the other line, and that voltage is unwanted. That's just noise. That can affect how we clock things. It can affect analog signals. However, there's also ground bounce. And ground bounce, I've heard a lot just referred to any noise on your ground plane. But what it is when two return current paths overlap. A common way of having this is splits in your return. So as these signals travel, their return has to travel back to the left. And they hit this split and they go, I got to get over there. So they're going to jump the gap. They're going to go around this. In any areas where their returns are overlapping, you're going to get noise coupled between them. That's going to show up a lot like regular signal side crosstalk. And the final one is noise in your power delivery network. Again, I'm going to mention PDN a lot because it's so important. If your signal is referencing a layer with cavity noise on it, between your ground and power, for instance, that noise is going to couple to any signal vias along the way and potentially even traces that are returning on those layers. So the basic design rules I followed between these designs is on the bad design, I have these return path discontinuities, right? Here is that split between my two grounds. And we have these signals referencing that ground, and they're going over that split. And we just saw the return currents are going to be bunched up. And not only that, they're really tightly spaced, routed a long distance with each other. It's a lot of crosstalk that's going to happen. Also, how I used my signal layers. I didn't give a lot of thought in the bad design. I went to these internal layers, cyan and pink here, and I just routed my signals. And they're all very tightly spaced. No, not a lot of thought was put in there. Whereas on the good design, you can see when I go down to inner layers, I immediately try to get these as far away from each other as possible when I'm routing outside the microcontroller. And so two very quick simulations were run in SI wave. And here we're looking at the near end crosstalk. Near end crosstalk is inevitable. You'll always have it. We just want to make sure it's within a certain noise limit. And we see indeed there is a lot more violations on the bad board. But what you'll notice is even though I had the best intentions in the good board, there are a couple of areas that violate. Again, simulation is so important to pick out these little things. And maybe these are unimportant nets. Maybe they're very important nets. That's the whole point, is diving into your sim to see what is actually going on. However, the most notable difference here is in far end crosstalk. Far end crosstalk, unlike near end, you can avoid. It can be completely eliminated in strip line or inner layer signals with a nice, even isotropic environment. And so you'll see everywhere this bad design is failing, warning me. And so I did a really bad job of routing on this bad design. But in the good design, again, we see, yeah, there are some areas with violations or warnings that we should look at. Little tiny areas with warnings. Again, maybe just increasing the spacing a little bit, but simulation is very important. Next, we're going to talk about the PDN again. And in this case, we're going to look at emissions that are going to be radiating from our board. What is this and why do we care? This is going to be the cavity noise in our board that ends up exiting our system. So the most common way to get cavity noise is having a signal routed on one layer, and we have to go down to another layer. So we go through this via. As it goes through this via, there's some inherent inductance. And so as you're switching across that inductance, there's some voltage that's going to be developed across these planes. That voltage isn't just going to remain here. It's going to spread in all directions. Call these like spreading voltage wavefronts. If there's nothing to stop them, they're going to hit the edge of the board and they're just going to radiate out. And this is a very popular way of getting near field emissions that can affect a lot of things. And so what we do is we add what's called return vias. Anytime you have a signal via, by placing a return, now this can be either power or ground, that's a little outside of the discussion today. But the point is, this is a very low impedance connection for the signal. And so again, as these pink voltage waves travel away from the signal via, they're going to hit this return via, see basically a short, and it's going to reflect negatively. So the voltage wavefront propagating from the return via is just in the opposite direction. So if it's close enough, these fields basically overlap everywhere. And so the return via, instead of like maintaining impedance or whatever else you might have heard for these vias, it's really just to cancel the field spreading inside of any cavities that you have. And design rules, again, this follows exactly from resonances. But again, bad design, this further spacing of the planes means more inductance for that via between the planes. That means a higher voltage can develop between those planes. So magnitude is a thing. So minimizing the spacing also helps minimize the actual magnitude of those voltage wavefronts. And then the via fill. Again, we've already talked about this, but adding a lot of vias when you're done with your design, having nice ground vias next to signal vias, and then when you're done with your design, sprinkle in as many ground and power vias as you can. More vias suppress more noise, and the smaller the spacing of those vias means that you're going to be attenuating or, damping a lot more higher frequencies. So how do I test this? Now we're getting into the full wave EMC plus simulations. So I imported this board into EMC plus, and I added a current source near the microcontroller. This is just going to switch a current between the power and ground planes. And again, I'm assuming a 1 nanosecond rise time, and we're peaking at about 8 amps, right? This is a worst case assumption. I'm switching all the pins. They're drawing a lot of current, but it gives us a worst case. And what I'm measuring is I have 2 probes along the edge of this board. One of them is just a statistics probe. We're gonna be able to do a plot to see the magnitudes with respect to frequency. And the other one is a very pretty animation probe that we can draw a lot of insight from. So first, let's look at the boring result, right? Let's look at the plot. And exactly what we talked about before, the good PCB design with the tight vias, a lot of vias, attenuates a lot of these frequencies. We only start seeing a peak about 3 gigahertz, which is way outside of any bandwidth of signals that we're using in this board. And again, the bad board, not a lot of vias, not a lot stopping those spreading waves from exiting our board, and boom, look at all the energy that's being dumped out in our environment in this range of about a couple hundred megahertz, which is usually right in your switching bandwidth frequency. So tighter via spacing, you block a lot more of the frequency content. More vias just means more cancellations. So the pretty way to look at this is we can look at the fields. Keep in mind, these are both playing at the same time. This is the same time scale and the same exact magnitude scale between these. This bad board is just shooting energy off the edge here the entire time. We see it consistent. We can't even see the fields here on the good design with the same scale. You'll notice some developing later. There's a couple of weird peaks, and that's probably areas where the vias were spaced a little bit farther. A lot of what you're seeing at the end of that good design, though, is just a bit of a numerical instability in this simulation that I did. So if I were to go in and hunt that down and fix that, we would basically see no fields being ejected from the edge of that good design. So again, PDN, so important. Suppressing resonances, so important. Here, this analysis, I am calling microcontroller header noise. Really what this is a demonstration of noise that you can get from your connectors, wherever you're launching a signal off your board into, say, a harness. And a header is inherently noisy. It's a terrible way to send signals, but it's nice for little Arduinos and whatnot. So what is it and why do we care? Well, just like we talked about in crosstalk, say we have this harness with 3 signals and a ground that's connected in this order. The ground's way off to the side. If we consider a signal on signal 3 here, it ultimately has to return back to its reference, which is ground. But to do that, its fields are going to spread way out to get to this ground. And in the way are these other 2 signals. So we're going to get crosstalk on those 2 signals, as well as 3 signals sharing the same return path is ground bounce. So we've got signal side crosstalk and return side crosstalk here. The radiation from these fields spreading couple onto everything in the area, including the connector. And if it gets on the shell, onto the shield of your harness, you've induced common noise. And that is exactly how you end up failing EMI. So connector launches, always have to pay attention. Everywhere, make sure that you pay attention to your return paths, but especially when you are launching signals off of your board. The major design rule that I followed is this: the bad design on the header. All of these green lines are pins for signals. And where you see the little blue sections coming in, we're connecting to a couple of pins for the ground. And so you can see, just like we showed before, look at all these signals and these inner ones. Look at how far they have to travel to get to a ground. And not only that, we only have a couple grounds for all those signals. And so to improve it on the good design, I used 1 ground for every single signal. And so at any given point, most of these have 1, 2, 3 grounds surrounding each signal pin. That should help contain the spreading of those fields. So how did I test this? I made the assumption that I'm going to drive 3 signals. So I'm assuming 3 of these pins, we are using like a communication bus or something like that. And you can see the 3 signals I injected here. I also want to monitor 3 unconnected pins, these gray ones. These are just going to be like pins that aren't necessarily switching at that given moment, but we want to see how much noise is on them. And we can easily see there's only 2 grounds here, and we got 1 ground for every single signal in the good design. In EMC Plus, what I did is I cut a chunk out of each of the boards with just the header area, and I used M-harness, which is a really nice way of setting up your conductors, where you just draw lines and then you assign conductors to them. And so if we look at the cross section of the bad design, we see all the signals that I'm driving, and there's only 1, 2 grounds in that harness. The good design, on the other hand, has a ground for every single signal in that harness. In addition, because the good design has termination resistors on it, I wanted to make sure that the signals indeed were terminated. So I added a couple of 50 ohm resistors to this board to make sure it's properly terminated. To measure things, I placed a couple voltage probes on all the signal lines that we're looking at. And then, not shown here, there's a little cube that I put around these pins, and we're going to see another pretty animation to really see what is going on here. So by looking at the near field, we see exactly what I was talking about. This is what we want to avoid. Same magnitude, same time scale. This is flashing like Christmas lights over here. Those electric fields are bouncing around and not necessarily constrained to the pins on which the signals are. They're bouncing around, sharing energy with everything in the area. In the good design, where each of these has 3 grounds surrounding it, look at how concentrated that energy is from our signals. There's a little bit of flashing. Yeah, you're always going to have noise, but everything is so well constrained here. And if we look at some of the voltage probes, we see the huge, huge difference this makes. Our blue line here, in this case, is the signal that we are switching. It's just a quick step signal. And in purple, we see on the good design, that tends to follow the exact same signal that we expect. What's cool is we get this little dip and this little peak, and those are the times at which one of the other signals switches up and down. So kind of neat. But in the bad design, look at all this noise. That is a crazy amount of noise. And not only that, there is this DC offset. Now, this may be something numerical. I have to investigate this a little more. But if we take this at face value, this is sitting around 2-ish volts. If we're trying to clock this signal, what's it going to clock as? A 1 or a 0? Well, I don't know. It depends on the receiver. And so this range for your signals is really bad to be in. And if we look at one of the unconnected pins, the ones that aren't currently being driven, because they're not being driven, we expect them to be sitting at about 0 volts. And in the good design, yeah, that's exactly what we see. Headers are inherently noisy, so we do have a little bit of noise, but it's so insignificant. And on the bad design, look at all the noise, an insane amount of noise. Even if we ignore the DC offset here, which may be something numerical, all of these AC signals are from these signals switching nearby. And so connectors, whenever you're leaving your system, pay attention to your return paths. The final analysis here, not related to signal integrity in the EMC necessarily, but electrostatic discharge is another thing to really pay attention to in your designs. What is it? Why do we care? Everyone knows what ESD is, whether you know it or not. You're walking around in your socks, you go to touch the door handle and you get a spark. That's fine, but you don't want that to happen when you're handling a board, because it's a lot of voltage that happens in a very short amount of time. So we arc to, say, a metal connector, and your metal connectors are usually connected to something like a chassis. And that's what this outer yellow place is, a little chassis copper. But because these are broadband, which means high frequency content and low frequency content in these zaps, we don't really care about emissions. What we're caring about is how much energy from that zap is going to leak into important areas of our board. We could induce voltages and currents on signal traces or power traces that go into a chip and blow it up. That's the major major issue. And the specs for ESD is usually about the total energy delivered. So it's not necessarily just the peak voltage, but how long a peak voltage lasts. The major design rule that I followed here is this separation between chassis ground and my local ground. And so we see the symbols. Local ground is what I'm returning signals on, and chassis is just our chassis. It's what's connected to the metal outside our board. And in the good design, the shields go to chassis, like we said, and these grounds are just used for the signals or the DC offset in the case of our Ethernet. And on the bad design, I just connected both of those to my local ground. I said, I'm just going to use chassis for my mounting holes. I'm going to connect these shells to my local ground. To test the consequences of this, again, EMC plus, because this is kind of a full wave thing that we're doing. And this is how you would do an ESD test setup in a lab. So we have this high resistance tie from our chassis back to our ground plane that we constructed. And all of this mess over here, just a bunch of resistors, inductors, capacitors that generate that spark. And so it goes right up to our USB connector. And what we're measuring, there's a couple of voltage probes I scattered about in the area. And we're also going to look at an animated current on the surface layer to show what that current is doing when it gets zapped. And so starting off with that animation, again, same time scale, same magnitude, what we see is because the spark here can go right into our local ground, it's going to bounce around in this design a lot. And so that's why you get all these little flashes happening everywhere in the design over a long period of time. In the good design, because this is tied to chassis and not to local ground, we get an initial huge spike of current that's all localized to my chassis connections, and then it quickly dies out. So we expect not a lot of the energy to be delivered into our system. And indeed, looking at the plots, the good design in red, the difference between our chassis and our local ground, we have a much higher voltage for a longer period of time. That means the voltage is going to be located on that chassis and not so much on our local ground. Whereas the difference between chassis and local ground on the bad design is like 0 volts. So everything on chassis is pretty much everything on the local ground. If we look at, say, the power net, the 3.3 volt net, we see in the good design, again, we do get some energy coupled, maybe about 0.5 volts initially, but it quickly dies out to 0 within like 10 nanoseconds or so. Whereas in the bad design, because we're allowing that noise to just bounce back and forth on our ground plane, it's much higher amplitude. It exists for at least hundreds of nanoseconds. And so in this case, when you simulate, you have to say, is this going to deliver too much energy based on the specifications of my chip? And so not SI, EMC, but this is more so, is it going to damage anything on my board? So wrapping all of this up, the conclusion. So what the efficacy of just using design rules alone? Even a professional signal integrity engineer can design a board that performs better, but still fails what we ultimately want. And so in this table, we see exactly that. The bad PCB design violates pretty much everything that we wanted. But even the good design, we saw that the PDN impedance was too, we failed it for the microcontroller. We saw a couple of violations with our crosstalk, and the others performed pretty well. Maybe the resonances and chassis is something we could look at. But overall, the good design did better, but it is not enough to meet all of our expectations with just design rules. So how can you ensure that you have a successful design? EMA has a wide range of experts, everything from lightning hitting planes all the way down to like ESD simulations on the die of a chip. So you could reach out to us and say, here's a design, can you run simulations on it and see what the worst case expected emissions or something is? And we can run those sims for you, give you suggestions if there are any failures. You can also reach out for a design review, which means you send us your board files. Someone like myself or one of the other SI EMC engineers will visually inspect them, look for issues like what you saw in this presentation, and suggest fixes. And if you have time and budget, we can do a couple of quick simulations as well. You can also reach out to us. I just recently created a PCB design rules training. It's about 6 hours, but it can be tailored for your team. So reach out and we can go over all of this in a lot more depth. And finally, if you're a classic engineer like doing things on your own, you can purchase both of these programs that I showed you here, SI Wave, EMC Plus. These are both available from ANSYS. And we see in this little cartoon, your designs plus our expertise can help you ensure that you have a successful product. And just wrapping up, a couple of really good resources. Because I went through these slides very quickly, lots of information being dumped at you here. These are a couple of things that got me into the field initially and are just excellent resources for anyone doing board design and you want to understand what's going on. First, Signal and Power Integrity Simplified. Bogatin, this book is like the Bible, basically, for SI and PI stuff. As well, Bruce Archambault, he's the president of IEEE for Signal Integrity. His design for real-world EMI control really helps you understand how fields are spreading in your board. What, not just voltages and currents, but what are the fields doing? If you don't like reading, I don't always like reading, you have a lot of videos and talks that you can look up to. All of these ones I list here are available on YouTube for free. Bogatin, Rick Hartley, Susie Webb, all excellent people to listen to. Some of these go up to like 2 hours just talking about grounding, and it will change the way that you approach your designs. And so with that, I will leave this slide up and we can move on to questions that anyone has.
Excellent. Thank you so much for such an informative presentation, Ryan. Like you said, we can now transition into the Q&A portion of the webinar. So as a reminder, attendees are encouraged to submit any questions to the team's Q&A feature to be answered at this time. At present, I don't see any questions in the Q&A queue. So while we wait for our audience to submit their questions, your presentation did inspire me with a few questions. The first one is, will we be testing these boards physically in the lab?
Yes, actually, I have just now kind of secured the fabrication and assembly quotes. So we're going to get both of these boards built, and even the stuff we couldn't get to in simulation, we're going to go in our lab here and do a whole host of E3 effects. So signal integrity, EMI, EMC, ESD, and anything else that we can think of.
Great. I guess another question for you would be, if we can't hit a 1-to-1 signal to return ratio in our connectors, how can we ensure a low noise launch in our harnesses?
Yeah, so when we talked about that header noise, I said that I had one ground for every single signal. In real life, that is almost never achievable, right? You have size limitations, weight limitations that limit the number of pins, and you need to launch a bunch of signals. And so 1-to-1 ratio is the goal. However, I usually in most designs would accept up to like a 3-to-1 ratio. So 3 signals sharing a return. 2-to-1 is even better, of course, but anything above 3-to-1, you should pay very close attention, do your simulations, make sure that there's not going to be too much noise there.
Great. Okay. Another question that I had was that you mentioned that tying chassis and local grounds together isn't necessarily a bad thing. Can you expand on that a little bit?
Yeah, so in the ESD section where I broke up the chassis and digital, and I said, keeping the ESD energy on that chassis is important. I know there's probably at least one attendee here today who I just did the training, PCB design rule training with, that is probably like, Ryan, you just told us something different. And this is where signal integrity, EMI, and other effects kind of butt heads a little bit. And so if you have, it all boils down to, there is no such thing as single point grounding with high frequency signals like digital. So if you only have high frequency signals in a board, tying your chassis and local ground together is absolutely fine. You're not going to get any problematic ground loops. Ground loops really become a problem here when you are dealing with lower frequency content. And so there is this trade-off. By tying things together, we give ESD a direct access into our local ground, which can be problematic. That's usually for like connectors that are outward facing. So if you have just boards inside of an enclosure, no ESD risks, absolutely tying chassis and local ground together is perfect. We can balance these things by using stitching capacitors, which is also called like frequency selective grounding. And by stitching chassis to our local ground through capacitors, that can help damp out some of that ESD noise coupling into our system. It only allows the highest frequency content to pass, which in an ESD strike is just that initial spike of energy. And even then, the inherent inductance and everything in those capacitors can help bleed off some of that energy.
Excellent. Thank you, Ryan.
Yes.
I don't see any other questions currently submitted in the Q&A feature, but I do see an attendee with a hand raised. So please do feel free to submit your questions in the Q&A tab. We do still have about 13 minutes left in our current webinar slot, so we will hang around here for a bit longer. If anybody has any questions, we'll be here to answer them. But thank you very much.
Yeah, and I'm curious, can we, for anyone who has their hand raised, I don't know if they can just turn their mic on and chime in or whatever. Maybe the question's a little bit too complicated to ask through through the chat.
Yeah, unfortunately, I think we have the settings for today's webinar enabled so that no attendees other than yourself and me can speak.
So Chris, Chris, if you could write it either in the chat or I'm always available if anyone has questions. Shoot me a message, ryan.french@ema3d.com. More than happy to answer any questions that you have, either from this presentation or just in general. As long as it's just a couple minutes for me to answer a question, it's not a problem. Okay, I just saw a question come in here from Jerry. A so-called a ground ring floating around the edge of a PCB is bad, I think. Yes. Any kind of floating metal in general is a bad idea, but that ground ring that you may be referring to usually is related to those stitching capacity, or the stitching vias and the via fills. And so one of the last things you do in a design is you fill, like I said, you put as many ground and power vias as you can in your board to eliminate those resonances. But just in case you're not fully constraining those fields, what you do is you put via rings around the outside of your board. You'll see this sometimes. It's usually just ground vias spaced evenly around the edge of your board, just so that if any waves do get to the edge of that board, they'll be reflected back in. So yeah, ground rings, any kind of ground, don't leave it floating. Make sure it's tied at least with one via somewhere. Okay, let's see here. Greg, how do you come up with the power plane impedance limit? Yeah, I mentioned that there's a way to calculate this. So roughly what you think about is your Kirchhoff's law, V equals I Z. Z is impedance in this case, not resistance, because we're doing AC. But if you rearrange that for the Z, your impedance, it's V over I. So what are those V and I? That V in that case is the amount of voltage noise you can have on your board. And that's up to you to decide. 5% is pretty standard. So that would be, in my case, 5% times 3.3 volts for that voltage. Under that, the current term is going to be the transient current, the maximum amount of switching current that you expect switching in a given IC. Like I said, PDN impedances differ from place to place on the board and depending on the IC's needs. So yeah, V over I, where your V is your noise voltage, I is the maximum amount of switching current that you expect.
I see another one here, Ryan.
Yeah.
Are these all the analyses we would need to do to test our board, or are there more analyses that you could do?
Yeah, man, there's a whole host of tests that I can do. The major ones I start with, I always look at stackups and power delivery networks, of course. Doing those PDN impedances is a major one. Resonances is a good one, but there are some ones that we didn't touch on. So in EMC plus, like a full wave solver, you can also look at, say, emissions from a given cable. Say you know what your harness looks like, how it attaches to your board. We can run that entire length of the harness and get EMI and what fields you actually expect emanating from that cable itself with all the properties that you know. Some other things, like if you have higher speed, say you're running DDR or something, there are quick analyses you can do in something like SI wave for I analysis, which basically just tells you how much noise you can expect in the time and the voltage region. So whole host of simulations you can do. These ones that I showed today were ones that ran pretty quickly and I think are probably most intuitive to a lot of people who are tuning in.
And Ryan, just to confirm, will the charts that you displayed in your presentation be available to attendees as well?
I hadn't put those together. If we want, I can get those over to you in say like a zip file. I'm not sure how we're sending out the PDF of this, but yeah, we can definitely do that.
Okay. I see another question came in. Does it depend on the application of the board?
Absolutely. Yeah. So if it's a cheap board, very slow microcontrollers, maybe you just don't worry about PDN analysis or something like that. If it's only high frequency content in your board, you're absolutely sure about that. You can also avoid doing like ground studies and looking for ground loops, things like that. So yes, it highly depends on how complicated your board is. Not sure if we'll get any other questions coming in, but
yeah,
great, awesome questions, everyone. These really hit on some of the important points that just couldn't quite cover in all of the content today.
Yeah,
like
absolutely.
I said, always available to answer any questions you might think of later today or whatever. Shoot them my way.
Yeah, thank you all so much for your time. I think we can go ahead and conclude today's session. So like Ryan said, of course, if there are any other questions that we didn't get to answer today during our webinar, you can always feel free to reach out directly to myself or Ryan over email or through the ema3d.com website. As a reminder, all registrants will receive an email from EMA with a link to the recording of this webinar, along with a copy of Ryan's presentation. Next up in the EMA Solving Electromagnetic Challenges webinar series is Production Grade Full Vehicle Electromagnetic Simulation Services, which will occur on December 17th at 11 a.m. Mountain, 1 p.m. Eastern. Thank you all so much for your time and attention, and I hope you have a great rest of your day.
Thank you, everyone.